How do I interpret FFT magnitude and phase for signal analysis? Imagine you have a complex sound or signal and want to understand its hidden components. The fast Fourier transform, or FFT, helps you do just that by breaking down signals into their basic frequencies. When you look at the FFT output, you see two main things: magnitude and phase. But what do these really tell you about your signal? Let's explore this step by step. First, think of the magnitude as the strength or loudness of each frequency component in your signal. If you see a tall peak at a certain frequency, it means that frequency is very present or dominant in your original signal. For example, in audio signals, a high magnitude at a specific frequency might mean a musical note or a tone is playing loudly. To get this magnitude, you take the absolute value of the complex number that the FFT produces at each frequency. This helps you identify which frequencies carry the most energy or power in your signal. Now, the phase is a different story. It tells you about the timing or position of each frequency component relative to a starting point. Think of phase as the shift or delay of a wave. If you imagine two waves of the same frequency, their phase difference determines whether they add up or cancel each other out. The phase is calculated as the angle of the complex FFT value, which shows how much the wave is shifted in time. This is especially important when you want to reconstruct the original signal accurately or analyze how systems modify signals. Both magnitude and phase work together to give a full picture of your signal. The magnitude shows what frequencies are present and how strong they are. The phase shows where those frequencies start in time. Ignoring phase can lead to a distorted or incomplete reconstruction of the original signal, especially in systems where timing matters a lot, like control systems or communications. Keep in mind that FFT results are based on discrete samples, so the frequency resolution depends on how many data points you use and your sampling rate. For signals with real values, the spectrum is symmetric, so you usually focus on the positive frequencies. Also, small magnitude values can make phase readings unreliable, so only interpret phase where the magnitude is significant. Using windowing functions and zero padding can improve the accuracy of both magnitude and phase measurements by reducing spectral leakage and increasing resolution. In practical applications, understanding the magnitude helps you identify dominant frequencies in signals like power systems or vibrations. The phase helps in analyzing how signals are shifted or delayed, which is key in control systems and digital communications. For example, in fault detection, shifts in phase can reveal issues in machinery. In modulation, phase information is used to encode data. To sum it up, the FFT magnitude shows how much of each frequency is in your signal, while the phase reveals when those frequencies start. Both are essential for a complete analysis, allowing you to interpret, reconstruct, and understand signals in electrical engineering tasks.